talked about the classical methods of subset selection.
We're looking at the R Studio.
Oh, sorry. I didn't put the zoom there. There you go. Classical method. Okay, the Mac is not working. I'll try to speak loud. Can everyone hear me? Okay. Okay, so we talked about subset selection last time, and the idea is to identify a group of subsets of the different models and try to choose the one that best explains the data. But if we have like too many variables to choose from, for example, tens of thousands or millions, then it's gonna still be very computationally intensive to do that. So ideally, we do want something that can just let us put in all the variables and then just tell me what the model should look like. And some modern methods are trying to cover that. So this is what we're going to talk about today. It's called shrinkage, or regularization. So these are the idea of going back to choosing the coefficients. So when we are doing model selection, essentially what we're doing is to identify which of the variables are more important than others in terms of predicting the data. So we can also try to do that by adjusting the coefficients. Like those that are less important, they could have like a smaller coefficient or even zero, right? So that is what shrinkage and regularization is doing. It goes back to when we're doing the ordinary least square, when we are generating the model itself, determining what the coefficients are, and we do something in the objective function of the optimization to introduce the bias and variance trade-off into that model. So let's see how it works. So first of all, there's the ridge regression. So we go back to the ordinary least square. When we're doing regression, essentially we're trying to minimize the residual sum of square. To determine all the betas. So residual sum of square looks like this. So this is what the ordinary least square is doing, but it doesn't take into account the number of variables, the number of coefficients we're including, so that it might have the problem of the bias and variance trade-off. It's not considering the increase in variance as we increase the model complexity. So what the ridge regression is doing is to adding an extra term. So we do the minimize with extra term. So it's lambda times the sum of the square of all the parameters. And this lambda is called tuning parameter. Okay. So this whole term becomes RSS plus and this term is the shrinkage penalty. So this, intuitively, what it does when we're minimizing this whole term, what the shrinkage penalty is trying to keep the betas small, right? So that is shrinking the betas. And if we write everything together, conceptually, it's going to be, so again, this is the RSS. This is the shrinkage penalty. So when we're determining the betas, we are doing the minimization of this whole thing. So for this part, we're trying to make the betas large so that we have a better, like a smaller RSS. We have less error. But then for this part, we want to make the betas small. So in this way, this whole function would balance out by maintaining the betas that are important for prediction and shrinking those that are less important. So that is similar to a model selection, right? Selecting essentially which variables are more important than others. Yeah.
When you say shrinking the beta, do you mean like the actual quantity of the intercept?
Not the intercept. Intercept is like the constant value, but betas is like the coefficients.
Sorry, yeah.
Yeah,
So
like
just
the
by shrinking them, you're making the coefficient smaller, so that term has less power overall in the
exactly.
scheme. Okay.
Yes.
Okay.
I have a question.
Mm-hmm.
So how does it exactly shrink the beta? Is lambda negative or?
So this whole term is lambda should be positive, and so this is the value that we minimize when we determine the data. So when we want to minimize it, this term wants the betas to be as small as possible, right? And this term wants the betas to be big. So only those that are important, like they're more important in this part in terms of decreasing the error would still maintain large. And those that are less important will be shrinked by this. So betas that have an important effect the betas that have an important effect will try to stay close to the true value, while the betas that are not important will shrink. Okay? And also to note that when lambda is 0, the penalty term has no effect. So it means that it's still an ordinary linear regression without the ridge. So how do we determine lambda? Okay, no space to write. Here. We determine the lambda by cross-validation. Okay, it's like tuning the model. So we select the best lambda that makes the model predict in the best way. So for ridge regression, it has one disadvantage. It can be difficult to interpret, especially when K is large. Because the beta would shrink towards 0, but don't get to 0. Okay, any questions about ridge regression?
K is the beta number of samples?
K is the number of betas, yes. The number of variables, or, yeah.
Can you explain what interpreting would actually look like?
Yeah, so when you interpret a model, it's essentially more about how you interpret the coefficients, right? What does each coefficient mean? So those variables that have betas that are super small actually means that they might not be that important for this model. But if you have a lot of them and you can't tell which one is less important, then it can be hard to interpret it. Although the model would predict well, it tries to shrink something, but doesn't remove it. So then it would be a bit tricky to interpret those variables. Okay?
One more question.
Yeah.
Does the value 0 and 1? Or
No, it can be anything. Yeah, it should be greater than 0, but it can be very large. So usually we test a bunch of possibilities. Okay, so another similar method is called lasso regression. It looks very similar. It's just the penalty term that is slightly different. So we're still minimizing the RSS. But the penalty terms, instead of using beta squared, it uses the absolute value. So absolute value instead of squaring. So the major difference between lasso and ridge is that when lambda is large, in lasso, the betas will be forced to 0. So they're actually choosing the variables instead of just shrinking them. So it'll be easier to interpret when we have a lot of variables. And still, we choose the lambda term via cross-validation. Okay, any questions about lasso? All right, then let's see how to perform these in R.
Can I ask real quick, how do you actually choose the lambda term via cross-validation?
So you try different values of lambda and then run cross-validation for each of the model, and then we choose the model that has the lowest mean square error when predicting. So I'll show this in R very soon. Let's see. So these are the packages that we're going to use today. The GLN-net is the major package that allows us to do the ridge and lasso regression. And I'll walk you through, first of all, how to do the cross-validation. So we're still using the data set that is called credit, like last time. ID column.
Can you scroll up a little bit just to, yeah, to see the package,
Mhm.
please?
Is the font size okay for everyone? Okay.
Thank you.
Mhm. And then we put the X and Y's into matrices. So this term here removes the first column. So you can see that the X doesn't have the ID column. Oh, it already doesn't have, so it doesn't have the balance, the first column. And the balance will go into Y. Okay.
Could you have taken away the balance column in that line 11 as well?
Hmm?
In line 11 where you take away the ID column, could you have also taken away the balance column?
Since we still want the balance here in Y, we're not taking it out.
Okay.
Yeah, just separating them into X and Y.
Okay.
These are for the cross-validation. So this is how you do a ridge regression on a certain model. You put in the matrices. Okay, so the lambda is exactly the tuning parameter that we're talking about in the function. And alpha is what determines whether this is a ridge regression or a lasso regression. So for ridge, it equals 0. If you want to do lasso, it's going to be 1. So we're doing ridge right now. And lambda is 0. What does that mean? What kind of regression are we doing? Yes.
Just RS.
Yes. So just linear regression. And we can have a look at the betas. Sorry, I didn't run it. Coefficients are here. And let's see if that's similar to when we just run the linear regression. Okay. You can kind of see it, right? They're very similar. It's hard to put them together, like on the same page, but yeah, basically the coefficients are similar. Okay, now we go into the cross-validation of picking the right lambda. we're going to choose the lambda that gives the lowest test MSE. So on the, we will record all the MSE in the, when we do the k-fold cross-validation, we get the one on the test set. So the steps would be, first of all, select a value for lambda. Then second, perform a cross-validation or using k-fold. And then obtain the average test MSE. And we repeat steps 1 to 3 across a range of lambdas. And finally, we select the lambda, which yields the lowest average test MSE. Okay, how do we do that in code? This is a function where we have an input number of folds we want to have in the cross-validation, lambda, and alpha. So first of all, this is also a refresher on how to do cross-validation. First of all, we need to divide the data into the folds, right? So we do this by sampling the vector of 1 through the number of folds. And then sample it how many times. It is the total number of the observations.
So are you multiplied by the number of observations?
No, like so in the sample function, this is the pool that you would draw from when you do the sampling. And this is the number of samples that we want to take out of it. And this will indicate if you want to replace everything you draw back in there or not. So in this case, since we don't have that many folds as much as the data, of course, we don't want to do that. So we do it by doing the replacement. Otherwise, we'll run out of the numbers to draw from here. Is that clear about this? Okay. And we define a vector to store all the MSEs throughout the cross-validation on different folds. And now we're going to run the cross-validation in a for loop through different folds. Okay, so in each fold, we need to identify what is the training data set and what is the testing data set. mind telling me what should be the training data set, and which one should be the testing data set? If n is the number of the fold that we're looking at right now.
Isn't that the testing?
Yes. So n folds would be the testing set, and then the rest would be the training set. So that's why we're doing this. Like, we're taking all the indexes that are not n, and these are the training data set. So for testing, we can just copy this whole thing here and just change this into equal to n. And the same for y testing. Okay. And then we run the ridge model. On which data set?
Training?
Yes. Okay, so the alpha and lambda are the inputs from this function. And we use this model to predict on what? What should we put in here? Ux. Anyone know it? Okay, it should be the testing set, right? That's why we're doing the cross-validation. We want to see how the model that we train on the training data set will perform on the testing data set. So we know how it performs on a new set of data instead of only looking at the MSE within the data that we already build the model on. And that will tell us more about the predictability of the model. And then we calculate the MSE. That is the true y's in the testing data set minus the predictions squared. And we store this in the vector that we previously defined. Okay? So that is one fold in a k-fold cross-validation. And then for our future analysis, to look at how the model is working, we want to store the coefficients. So this is just for storing coefficients for reference in the data for later. So these are actually might be slightly different from the coefficients that are actually generating those MSEs. But now we just use the full data set. Store the coefficients here. And we also want to store the average test MSE, right? So after all these loops, we have a bunch of MSEs in a vector through every fold, and we are storing, we're going to calculate the average of them. In a data table, so this is one column, and we also want to store the corresponding lambda. And we also want to store the coefficients so that we can have a look at what the lambda and the coefficients, how they're changing with each other. Okay? So this will be the output that we want to return from this function. So generally this function takes in one lambda, and then we perform the cross-validation, and it returns the corresponding mean MSE through all the cross-validations, and also the coefficients for this lambda, okay? Any questions about this? So how are we going to use this function to select the best lambda in concept? This one takes one lambda and calculates the average MSE, right? How do we choose the best lambda?
We run it for different values of lambda with different inputs and then choose the one with the lowest MSE.
Yes. So usually we select the lambda, the tuning parameter, by order of magnitude. So we'll have a bunch of ridge models to choose from, and we store them in a data table. So we run a for loop to perform what we just said, run through a bunch of lambdas. This is going to be in different orders of magnitude. Okay, so this L is going to be the different lambdas. to use the function that we just generated. The input would be the credits data set, and we're going to do 10 folds cross-validation. The lambda is going to be L. The alpha is going to be 0, since we're doing ridge regression. So the ridge models will be stored in here. Okay. Now let's see what happens. What happened? Okay, let's plot something to look at what happened. So all ridge models are stored here. We can have a look first. So these are the coefficients. These are the lambdas that we tested on, and these are the test MSEs that are generated from the cross-validation. Okay, and we're gonna plot the lambda against the average test MSE. Okay. See how it looks like. There's an increase in the test MSE when the lambda exceeds a certain magnitude. And what we want to do is to choose a certain lowest point in here, and that lambda would be the best, right? Any questions? No?
I have a question.
Yeah.
If you were to magnify the y-axis on that, not so I've only looked at like maybe 1,000, would you see a more pronounced dip at the very beginning of the log?
You mean like is the very beginning still like?
Yeah, like is there a
trend?
shroud in there that we can't really see because of the scale of the y-axis?
Yeah, it's not always increasing. So there's at
Okay.
one point it is the lowest. We'll see very soon. Okay, let's actually do it now. Let's try to choose which one is the best. Okay. All ridge models. We want to see which row has the lowest average test MSE. Okay. So it's the lambda equals 1. Okay, it is actually the first one that we tested. It's not always the case though. But it's also worth mentioning that you can see at the beginning, these values are actually very similar to each other. And we're going to cover that a little bit later. for plotting, to plot the coefficients, we want the coefficients to be not different columns, but in one column with different labels. So we do that by using this function called melt. So that is changing a data table from white to long. And there should be a corresponding function that does the other way around. Very useful tool when we're doing data analysis. So the IDs would be the ones that we still want to, the columns that we still want to keep. And all the others will be melted into two columns. One for their value, one for their names. We'll see how it, we'll see how it works out. Okay. So the first two columns are the ones that we want to keep, and then all the variables become something like this. The values are in one single row, and these are the names. Okay? So we're going to use ggplot. Define the data. Oh no, wait. Actually, I should change the name of it. Let me run it again. Let's call it all rich models long. Okay. Aesthetics would be, we want to plot the log lambda against values of the coefficients that are already in one column now. And that's why we're doing it, because we want them to be one single y in this function. And we define the color as the name of the variable, so that we have different colors of them and a bunch of legends indicating which variable it is. We want to plot it as lines. Okay. Here we go. So this is how the variables, the coefficients would shrink as we increase the lambda, right? And if you have a very large lambda, they'll really shrink to very close to 0. And we want to probably zoom in to see what's happening has set the limit of y. Okay. This is what's going on at the x-axis. So we can see that some of the coefficients would shrink faster than others. So these could be indicating how important they are to the prediction. So for example, this one would shrink faster than this one, right? So
When they will shrink,
mhm.
when they cross the y-axis, or
when they get closer to y-axis. So whether it's positive or negative doesn't matter about like whether it's important or not. But when it gets like in scale or in absolute value smaller, it means that the beta is shrinked. Because even if it's a negative value, but it's still quite large, it still tells you something about it, right? It's just the positive or negative impact on the predictor that you want to regress on. Any questions about this part? Okay, let's go on. So,
I have a question.
Oh,
So
yeah.
all the variables in the center are not important for the model?
let's say they are less important than others.
Okay.
Yeah. Less important in terms of predicting the model instead of interpreting them, right? It's a different thing. Also, the order of the shrinkage has nothing to do with how large the coefficient is. So, for example, this one, which one? Let me see. Yeah, for example, this one here is probably larger than the green one, but it shrinks a little bit faster than it. So how large it is probably has something to do with when you're interpreting it, it has a larger impact on the y value. But it could also be related to like the scale of the x value for this coefficient. So that doesn't have to do with how important this variable is when we're predicting the model, right? So it's important to keep in mind to separate these.
So there are a few variables like cards or I think married that they grow a little bit as lambda gets bigger before they shrink. Is that a normal thing?
Yeah, it happens.
Okay.
But they're not like growing too much. They're still like in a certain range, right? So I would say it's still like these are quite similar when they're doing this. But when shrinking, these are all already very small. Okay.
So, another question.
Sure.
Maybe I missed it, but when we took the minimum of the MSC of all of the lambdas and we found that the first lambda happened to be the best one, then would we take that value and then run the model?
Yes, that's exactly what I'm going to do now.
Okay.
Yeah. So I just run this line that we typed earlier. This is the lowest. Okay, now it's not 1 anymore because we run the cross-validation again, and the sampling is different. So yeah, it still starts at 1, but the best value is actually 1.5. So let's put it in. run the ridge. Let's just put this value in. So this would be our best model. So some of the variables coefficients are relatively shrinked, but it's actually not that seriously because we're not taking the lambda into this range, right? So this is the results that we have after running cross-validation and choosing the best lambda, choosing the best ridge regression model. And how do we do that for lasso? We're gonna use the same cross-validation function. All we have to change is the alpha. So ridge and lasso have different sweet spots for lambdas. So we're not testing the same lambdas anymore, but still in magnitude, in orders of magnitude. Okay, here, alpha equals 1. That's what indicates that it's lasso. Okay, so let's plot the same figures. Okay, so it's a similar trend, right? The test tendency would be similar within a certain range and then increase as the lambda become very extreme. And for the other plot, we still need to do this wide to long transformation. here. So it's still also a similar trend of the coefficients shrinking, but let's also take a closer look. So you can see that it's different from ridge regression, that some of them would just disappear, right? They just reduce to zero instead of being very close to zero. So lasso regression actually removes variables instead of just shrinking them. And this order of removing the variables could be similar to when we are doing the step backward selection. We're also removing variables, and the order of them shrinking or like disappearing from the lasso regression. As we increase the lambda, this order could be similar to when we were choosing which variables to remove first in backward selection.
Why we block log lambda and not lambda by 2?
Because we chose the lambdas in orders of magnitude, so only when we're plotting log lambda, this axis is going to be linear. Otherwise, the lambdas wouldn't be like the distance between them wouldn't be equal. So it would be hard to look at this. Well, you can have a look how it looks like if I remove it. Let's see. It would be like this. Kind of still follows the trend, but a lot of stuff will happen here, and these would be very far from each other. So yeah, it really depends on what are the values in your x-axis.
And the way we set the lambda, like it always need to be like that, 10 to something.
It's not a rule. You can also just test it on whichever values you want to. But I think this could be the most efficient way to test it, because probably at each order of magnitude, all the lambdas perform similarly. So that's why we're doing this search. Okay. And then we will also choose the best lambda. See what it is. So the best lambda is this, 0.12, and we can just put it in to the GLM net and regress on the full data set. Alpha equals 1 means that it's lasso. Lambda would be this value. Good. Oh. Typo. Okay. So this would be the best model with lasso regression. Any questions about this?
I think in the last class we talked about step forward and step backward, and I think I remember that you wouldn't typically do both of those. you would just do one? Because they would kind of give you similar.
Sometimes we do both.
Oh.
Like in the built-in function, there's the choice of doing both.
Okay.
So it's I think what it does is at each step it tries to go forward and backward at the same time and see which one is the best. So sometimes we do both. Yeah.
In this case, is it common to do both techniques that we just talked about?
Yes.
The ridge and the lasso?
Yeah. Also, it depends on your data set. They both have their own pros and cons, and I'll mention that a bit later. So you need to evaluate your data set to see which one fits it better. Yeah. Okay. So of course there are built-in functions that can do everything that we just done for us. So both the cross-validation and determining the best. Okay. And it is called cv.glnet. Oh, sorry, not capitalized. cv.glnet. Okay, and we can plot this model directly. This will give us a similar plot as before. This is the mean square error. This is log lambda. And these indicate that the best lambda is somewhere here.
What is the, like the 111s on the top?
Well, I don't know.
Okay.
It just generates automatically when you plot it.
And they said the two lines show the best.
Yes. Yeah. And it's also within the outcomes of the function. We can, we'll have a look later. Let's first look at the coefficients. So a bunch of results are stored in the results of the model. Let me see. How do I? That's how the data structure is like for the result from the built-in package. And to pull out the coefficients, there's this GLN fit. Yeah. See how it looks like. Right, so it looks similar to what we plotted when we do it manually. And let's see what is the best lambda. Okay, so it's 39. It's not the 1 point something that we generated before. Actually, it's because it actually didn't even tested those lambdas. So the lambdas that it tested actually starts around, let's see how, starts further away, right? It actually starts from like somewhere close to 40. And why does this function do that? If we go back to when we were doing everything manually, there's actually this range at this part that we have very similar test MSEs actually before 4, right? Before a certain threshold. So I guess what the built-in function is doing, that it actually knows the threshold, and everything before that is like very similar, so it would just test from that point on. So yeah, that's why it gives us a different best lambda.
And if you take the log of 39, it will be the 1 point something, or it doesn't matter that here is 39, but manually it was 1.5.
So these are different lambda values. So 39 and 1.5, but they should have very similar outcome. That's why the built-in function doesn't even test anything before 39. Yes.
So it's not a misleading result that it's 39, whereas when we did it manually it was like 1.
No, it's not. They have a similar outcome.
Okay.
Yeah. If you look at let me see if we can look at all the ridge models here. The test MSEs, they're very similar, right, before a certain range. And then after 39, they're jumping faster, right? And for the coefficients, it's similar. Like before 39, they're like similar, and then they just start to really shrink heavily. So that's what the built-in function is doing. It knows where the threshold is, where to start with, so that I can run faster, right? Okay. And we can do we can run the rich model with GLMnet. And now we use the best lambda from the built-in function.
Capital X.
Yes. So this is the best model that we obtained from the built-in function. And then we do the same thing for lasso. Alpha equals 1. So same thing here. The trend is also similar. this graph also looks very similar to when we're doing it manually. So this is the best lambda chosen for lasso from the built-in function. And we can also put it into the lasso model and regress it again. So this would be the best model from lasso regression. Okay? So any questions about ridge and lasso so far? So, we go back to here. So we have pros and cons of ridge and lasso. For ridge, it can be harder to interpret compared to lasso because it doesn't remove the variables but shrink them to a very shrink the coefficients to a very low value that is close to 0. Lasso has this advantage of actually choosing the variables, but ridge has one advantage that is quite significant, is that it deals with collinearity better than lasso, because when two variables are correlated to each other, but we're regressing them both on y, it's possible that one of the x contains part of the information of the other x, right? So in that case, lasso might just make one variable, just remove one of them, because it thinks that, oh, this information is enough. But ridge will still keep them because they're still part of the information in the other one that might be important. So that is one advantage of ridge regression that deals with multi-collinearity better. So there's another method that takes the best of both worlds. And you can imagine how it looks like. What do you think the objective function would look like in a function that takes both the advantage and both the ridge and lasso's advantages? What do you think of it? First of all, it's called elastic net regression. The idea of it is, why not both? Still minimizing the RSS. Plus something. So essentially, it just put them together. Okay? Just put the two penalty terms together. So this is the lasso penalty. This is the ridge penalty. Right? So still, we solve the cross-validation. For lambda 1 and lambda 2. So the computational complexity increases much faster because we have two lambdas to deal with. Okay? But it really overcomes the shortcomings of lasso or ridge. While retaining their benefits. So first of all, it keeps the feature selection quality from lasso. By allowing the betas to reduce to 0. And then second, it has the effectiveness of shrinkage. From ridge regression. And it's very good at handling highly correlated variables. Okay? So feature selection, shrinkage, and correlation. Okay, any questions about this? Okay.
Is there like a good rule of thumb for having what k size is a good cutoff for like one method versus the other?
I wouldn't say ridge and lasso would differentiate in terms of the number of K. So both of them would deal with, I think, tens of thousands or millions, or even larger, even larger data sets. But I think it really depends on if you want more interpretability, or if you think a lot of the variables might be correlated to each other, you might want to use ridge regression versus lasso.
Okay.
Yeah.
In terms of this elastic
Mhm.
combination,
Mm-hmm.
I guess is the complexity that is we're concerned about, that would be more of a, not so much related to the value of K, but maybe just the size of the data set? Or,
Yeah, the value of K, like the size, not the number of observations, but like the number of variables. If you have like millions of variables that you want to
Okay.
choose from, you will prefer using ridge or lasso or lasso net versus the subset selections.
got it,
Yeah.
okay.
But for subset selections, it's more classical, so it has more interpretability. It is actually choosing like one model versus the other, instead of like just putting everything in, and then you have a bunch of betas, and some of them might be like super small and would be probably harder to interpret, but it would still maintain the good predictability of the model. Okay. So let me quickly show how does the elastic net work in R. It is a bit complex. But it's really just about how to use the built-in function. So we will have one parameter called train control that just sets some of the parameters. Like we choose repeated cross-validation for this, because cross-validation is based on sampling, and when we repeat, you'll have a more stable sample, a more stable or centralized values of the MSEs, avoiding some extreme sampling of like a certain fold that is very extreme, and that can give you a crazy MSE, right? So it's like 5 folds and then repeat 5 times, and search randomly. And this one just tells it to record everything. Okay. And then the main function is called train. So you put in the data. Method is GLN-net. And these are some optional features. You can do the pre-processing. Here we use, I think this does like kind of standardize the data. And this one here sets the granularity that you want to test. And then you put the train control here. Okay. Let's run it. Wait.
Your train control should be train dot control.
Oh, yes. Thank you. Okay, it's running. So it's really testing all the different combinations. So the alpha is actually what determines the lambda 1 versus lambda 2. So we can put this back in the GLMNet. Let's see. Okay, let's first have a look at the coefficients. So do the cross-validation again. So we put in the alpha here, so it actually becomes a elastic net regression. Okay, so that's how the coefficients change. So it's still similar with the shrinkage, but some of them might also reduce to 0 as we increase the lambda. So then how do we obtain the best value? We can actually just directly use alpha and lambda from the train function. So just run a GLMNet. So you can see that for the GLMNet, the alpha doesn't need to be either 0 or 1. It can be something in between, and it becomes the elastic net.
I have a question.
Mhm.
When you run the function train
Mhm.
in elastic.net.best,
Mhm.
that creates the column best tune in alpha and lambda?
Yes.
Okay.
So it chooses the best alpha and lambda, and by choosing these two, it's actually essentially choosing lambda 1 and lambda 2. It's the same thing, it's just the function is slightly different in defining them.
Okay, so the function add those rows to your data set.
Yeah, so this elastic net best, let's see how it looks like. This one. Here, yeah, you have all these results. The best tune, it gives you the alpha and lambda.
Okay.
Yeah. So this is the best move. Where's it? Here. The best model from elastic net regression. And you can see the betas from here. It still works similarly in this case compared to Ridge and Lasso, because actually they are not very different in this case. But yeah, that's how you do it in R. And so to conclude what we learned this week, all these methods of selecting or regularizing model, they all have one same purpose, or like one same goal when choosing the right model. And what is that? Can anyone tell me? I mentioned this a million times every time I introduce one model. What is the one thing in common between them?
Minimize our S's.
Minimize what?
Like, isn't it like the between bias and variance?
Exactly, yes. So bias and variance trade-off. Let me go back to the. Okay. Oh, forgot to turn on full screen last time. Sorry about that. So. So these are all called decision theoretic approach. And the one thing that you really need to keep in mind is this bias variance trade-off. Total error versus model complexity. So as we increase model complexity, what is decreasing?
Bias.
Yes. And what is increasing?
Variance.
Yes. So the total error looks like this. And all these models, we're trying to select the models that doesn't only fit the data that we're training on very well, but can also predict very well. And that's when we're doing this kind of balance and try to find the optimal spot in here. So trying to push in both ways. So we want our model to realize the benefits of increasing complexity, but we also want it the other way. The model to penalize the cost of increasing error associated with variance. So, as we can tell from all the models that we introduced, there's going to be a certain part of the model that address this by trying to penalize increasing the number of parameters too much, right? So this is generally called the loss function. So yeah, you can think about it. What is the loss function for region lasso, also for AIC, BIC, and adjusted R-square. They will have their own loss function in their formula. Any questions about this?
Wait, can you just repeat? NIC and R squared also have loss function? Is that what you said?
No, AIC and BIC
Oh, okay.
and adjusted R squared. So what we learned last time.
Got it. Okay.
Yeah. Okay, so that's all the contents for today. Any questions? All right, so thank you for your attention.